proceedings.
Yeah.
Milind?
Good afternoon, everyone. Myself, Dr. Milind Vasnik from the Department of Periodontics and Preventive Dentistry. Welcome you all for today's program. National Science Day is celebrated in India every year on 28th February to mark the discovery of a Raman effect by Indian physicist Dr. C.V. Raman for his discovery. Dr. C.V. Raman was awarded the Nobel Prize in Physics in 1930. Science and technology play an important role in the development of our nation. It is an interdisciplinary topic encompassing science, technology, and their interactions. Science is a systematic enterprise that builds and organizes knowledge in the form of explanations and predictions about nature and universe. Today, on the occasion of National Science Day, we have with us our guest speaker, Dr. Abhay Patwardhan sir. I call upon Dr. Arun Sajjanar sir, our head of the department, to introduce our today's guest speaker.
It's my privilege and honor to introduce today's speaker, who is well-renowned research scholar. Dr. A. Patwardhan sir has obtained his MSc degree in chemistry in the year 1982 from Nagpur University. Subsequently, he has obtained his PhD degree in the year 1987 in the subject of chemistry from Nagpur University. He was holder of UGC as well as the Department of Atomic Energy Fellowships during the course of his PhD tenure. Subsequently, he joined MS Reckitt and Coleman of India Company as research associated at the research center located at Bangalore. Later, in April 1987, he joined Atomic Minerals Directorate for Exploration and Research, Department of Atomic Energy as scientific officer in the year 1987, and he was holding the designation of scientific officer till his retirement. His work mainly pertains to the analysis of geological matrices, which includes the rock mineral and beneficiations products at major, minor, and trace and ultra trace level concentrations for characterizing the geological materials leading to exploration of atomic and strategic minerals. He has led the mobile geochemical laboratories of Atomic Minerals Directorate for Exploration and Research since 1992 to different remote locations across the India. His field of interest mainly are the trace analytical techniques which are used in geoanalytical work, like the inductively coupled atomic emission spectrometry, atomic absorption spectrometry, inverse voltammetry, and fluorimetry. To his credit, he has more than 70 research papers. He is a reviewer of various journals in chemistry, the Journal of American Chemical Society, Journal of Atomic Absorption Spectroscopy. He is the member of Board of Studies on Chemistry, uh, BNIT, that is Vishwesvaraya National Institute of Technology, Nagpur, and life member of many professional bodies. So it's with these introductions, now I welcome Dr. Abhay sir to deliver his lecture.
Thank you. Thank you, Dr. Sajjanar. Hope I'm audible. Am I? Hello?
Yes, sir. Yes, sir. You are audible.
Fine. And and this first slide that I have put in, is it visible?
Yes, sir.
Fine. So thank you, Dr. Sajjanar, for an introduction. Well, since your institute situated at Nagpur, for me it is something like a distant homecoming. So not really requiring a welcome address there. I'm part and parcel of the city. Have been. When I was approached for delivering a talk on this topic, the first thing that came to my mind was nuclear energy, not only because I have been working with a nuclear energy institution or an installations, but in the context of eco-friendly and sustainable source, I do not find any, frankly, I do not find any other alternative at this moment. Because things that will slowly unravel. Let me start as regards why we are here. We are here discussing because of this particular person, Sri Chandrasekhar Venkat Raman. There are two photographs here, one while he was young and one while he was old. Uh, However, it is so joyful and heartening to realize that this is one occasion we are not celebrating anybody's birthday was caused by this particular. See, there is a major change in the attitude that we have seen in the scientific world. In the scientific world, what matters is what is the truth, what is the new findings, and this is to be commemorated. This is this and not just because a person has a date of birth and so and so. So this is one of the wonderful things about the National Science Day, that it is scheduled on a day when Raman's discovery of Raman effect was made public. He had been at it for quite some time. We'll go just, if you allow me, a just brief biography, so as to tell you and tell some of my younger students here that it's not always very big, and if things start at a very small level, people are now normal, but their thinking, their zeal, and their endeavor is abnormal, and that is what leads to some major findings. Having born in a very, I would say, not even a middle class, a lower middle class family in Tiruchirappalli, and he showed his efficiency, his liking to the subjects all through. This is how you can. I wouldn't read through the slides. I'll go through them quickly. This is how he progressed in early life. What made him famous? These are the two things. Discovery of Raman effect. However, our Indian mindset doesn't acknowledge anything until it has been awarded with something. But in this case, it did happen. There are many cases where our people have not been onto the podium. However, their contributions are significant. But in this case, it so happened that his contribution was significant. And by God's grace, he was also awarded a Nobel Prize. That's the first time an Indian scientist came to the forefront in the world. And for us, and the most wonderful part of it is that this entire Nobel Prize winning effort was not carried out in some very exotic, some very high end laboratories. It was his zeal, his personal effects, personal interest, and his continuous labor that made him that he did brought him to that level. Something that's in the mind. It's not nothing to do with the infrastructure that you have. If you have a mind which is inquisitive, the mind which is willing to put in hard work, and something that practically is in your mind all through, probably we may still have some more of such Nobel Prizes coming in days to come. This is how he progressed worldwide, and very glad to see he was also awarded a Bharat Ratna later. Of course, the subsequently other scientists also have been up to this. Now, what exactly is Raman? We have been hearing about Raman effect. Raman effect, in a very small nutshell, it's a chemical analysis method for solid, liquids, and gases, wherein the material is characterized by not getting in contact with it, and in a non-destructive method. In all other forms of chemical analysis, by and large, not all of them, by and large, non-destructive method is something different, because in all other cases the material concerned is either solubilized or made into a gas or solidified or coated with something else, so as to analyze it, make it analytically feasible, and then the results come out. But in that situation, what happens? The pristine structure of the material, right? The way the material was made, its surface, its bonding, everything is broken open. So at the end of the experiment, you do not have the material itself. This does not happen in case of Raman studies. The material remains intact in its pristine form. So that is one of the greatest advantages, as I see in a Raman effect. Consequently, I'd be shifting gear to another name here, Dr. Homi Bhabha, because we will be discussing about nuclear energy. A brief introduction as to what Bhabha was and what is the link between Dr. Bhabha and Sir C.V. Raman. In a way, if I may put it, we'll come to it later. In a way, Sir C.V. Raman was responsible for holding back Dr. Bhabha when he had come to India and put him as a professor at Indian Institute of Science, Bangalore. Dr. Bhabha could have been anywhere in the world and at his level and his stature could have been an spotted such an eminent person to be in India, brought him to Bangalore, got him onto the with some infrastructure, and then what mushroom was today as Department of Atomic Energy and Indian ISRO, Indian Space Research Organization. Just like Sir C.V. Raman, Dr. Bhabha also had a very passionate interest in science and in physics in particular. We'll come to that. See, one quote that he lived with, and this is one quote, this is the thought he lived with till his life, for his entire life. And he really practiced it in every sense. It's something that should ignite a mind, I hope. The best part is I care since therefore I cannot increase the content of life by increasing its duration. Obviously, that's a limitation with our human life. Then he proposes I will increase it by increasing its intensity. Intensity is efforts. That's what he did. At a time when there were only not more than 3 countries in the entire world practicing and following nuclear energy structures, India started on its own. India, under Dr. Bhabha, started on its own without any major support from the outer world, from the other part of the world. In fact, there have been cases where Indian progress has been looked down and was hindered. But this is one man, through his sheer ingenuity, efforts, and persistence, got over all the problems. Let's get to just a small biography of him. Why I'm showing you this? Because in today's world, it normally happens that when an institution comes up, be it a scientific institution, be it an educational institution, that institution is driven by some other motive. The motive is either to have some acquisition as regards fame, whether to have an acquisition or an authorization as regards large amounts of money, or third, if not, the personal gratification. In this case, as we go through, you will see none of this existed. There was no direct benefit to the person concerned. In fact, he has been one of the major donors in terms of his time, his money, and his property towards the country. This is one man who, had he not been in India, could have possibly, or should I almost say certainly, been a Nobel Prize winner in any while if he would have continued his work, what he was doing. Because the work that he was continuing with another researcher subsequently led to Nobel Prize. Bhabha came to India and chose to stay, and that is why he missed out on that. But what he built today is more phenomenal. Okay. So from here, okay, we'll skip this. These are some family history. It may not be so interesting. Apart from being a scientist, he was a painter, he was a musician, and all other things. Now, this is one letter which he urges, his father had sent him to UK to pursue the career as an uh, engineer. He did that, but he realized his liking and his mind is set on physics. This is what he wrote to his father. And obviously, after reading such a letter, I don't think there is any father who would refuse to support him, support his child. My success will not depend on whether what A or B thinks of me. My success will be what I make of my works. Beside, India is not a land where science cannot be carried on. He had such a confidence that India, I'm burning with a desire to do physics and I must do it sometime. It is my only ambition. I therefore earnestly implore you to let me do physics. That's what he did after completing his mechanical tripos. That is your present BTech degree equivalent to that. Then he shifted over to physics, did his work in physics. I'm going over the history. I'll come to what subsequently. Okay, we'll skip this. Sorry, just one moment. This is where this is one of his work, which could have led him to a Nobel Prize, which he had he continued. Theoretical physics under R.H. Fowler in Cavendish Laboratory. R.H. Fowler later on got a Nobel Prize, wherein a major part of the work was the work that was carried out by Dr. Bhabha. And being among the most eminent and wonderful minds, he was in touch with almost all the top scientists that time, be it Hitler, no, Hitler is not the Nazi Hitler, it's a scientist that's Hitler, or Niels Bohr and others. Now, but what follows that is the backdrop. What follows is his contribution in the coming to India. He is instrumental. Sorry, I'm skipping the slide slightly faster so that we can concentrate something more on other things. He was the one responsible for writing a letter to the Tata Foundation to fund it for starting what? Not an economically viable situation, but an building was not constructed or it was under construction. That entire institute functioned from Dr. Bhabha's own property, his own first home. That is TIFR first home was Tata's residential house, which he vacated for this thing and went to live on rent while drawing only 1 rupee as an rent for this entirely large property at that time. 1 rupee a month, because that was required to be part of the agreement. So this is the selflessness that has brought science to the forefront. We'll skip this. We'll go ahead. This was a man who was never worried about criticism. Minded, this is something very important because whatever you do, there could be criticism on either side. Some which drives you towards a right goal, and some which pulls you back. But he was one. He was not really bothered about criticism. Not a man to be daunted, and he had the persuasive power. He persuaded it, repeatedly got things done at an pace, at an speed and pace which is unheard of even today. Believe me, I'll just not here. I'll quote from an example. A major analytical instrument was to be purchased way back in 1950. Way back in 1950. That time, the transportation of instruments from other countries by air was not possible. By ship was the common feature, and there was a lot of administrative work to be taken up. Bhabha required that instrument to be there on Monday, while this was thought of on Wednesday. He saw to it that the equipment reaches the location on Monday and the work starts. The entire slogan behind the entire exercise was work should stop at any cost. That is the sort of thought these people had towards work and their commitment. Okay, let's skip this and we'll come to something else. There's a lot many one can say. Unfortunately, we had an early demise, 1966, Air India were Boeing 7 in Monteblanc, France. There are many theories to it, but let's not go get into them. But yes, this I would like, if Baba had not perished and then crashed, would have been in quite different India today. Probably he was about 30 to 40 years ahead of the contemporary world, and he could have taken us in terms of energy self-dependence much earlier. Now, question is, what is sustainability? Coming back, how to measure sustainability and how to manage sustainability. These questions appear very, very tricky, but believe me, there is nothing simpler than to think about sustainability. Sustainability is nothing but to control all your working in a manner that you live tomorrow and you live the next generation. Your requirements, your technology, your wants, all should be controlled and thought of so that they are not going to hurt your tomorrow and not going to hurt the next generation. Nothing more than that. All those lofty books about sustainability are the means as to how to go about them. But the basic concept is very simple. Yeah, it is the present and the future, the capacity to meet the needs of the present without compromising the ability of future generations to meet their own needs. And this is Bertland Commission, which was commissioned since 1987 for establishing sustainability of any industrial processes in the world today. Well, this is not pertinent, it's somewhere else in the slide. Now, why I'm coming to energy, sustainability has various different aspects. However, the mute point or the most focused point of any sustainability exercise is energy. Now, energy has got different modalities from which we can draw. We have heard a lot of renewable energy sources. Let's discuss them. Okay. As regards any queries in between or any things, please put them down. I'll be happy to answer them subsequently. Now, hydroelectric power. You can go through the slide. I can very simply tell you hydroelectric power and solar power are, in fact, solar is one of the most omnipresent energy option, followed by hydroelectric power. However, what is the problems? We'll come to solar later. Let's talk about hydroelectric. Hydroelectric power requirements are, one very simple requirement is that we require perennial rivers. Perennial in the sense, one which have got large flow rates all around the year. In a country like India, we have got only a handful of such rivers which are perennial. The rivers are normally in spate during monsoons, and by October or November, the flow rates are so low that it is not going to give you any amount of electricity. Forget even irrigation. Even for irrigation purposes. So this is one option which is very require large amount of infrastructure development. Yes, what it requires is that it requires large area which is submerged. Well, thankfully, India has got large surface area available to us as a country. We can afford it, but we can't generate perennial rivers. So, what perennial rivers we are having, we are harnessing them for energy resources, but other parts of the country we don't have. So, this is one option which is of limited use to us. Wind. Yes, wind energy is also very good, but here the vagaries of wind are far more larger. Uniformity of speed, velocities, quantum, and the directions all change very rapidly. So there are only few certain zones in our country, certain locations in our country where wind energy can be used and can be meaningfully used. Just putting up an windmill and trying to get something, say you get a small battery charge with the windmill, that is not our power requirement. We are talking about power requirements in gigahertz, yeah, gigabytes and mills. So these are options. Yes, these are options which are highly sustainable low in terms of cost, not much of any other issues to environmental issues, but they are limited because of the geographical locations. Solar, undoubtedly the largest uh, source of energy that's on earth could have been solar. We have got now over last some years we have gone, all the countries in the world have gone a large way on solar energy. We are seeing those panels. All these is fine, but if we have to have, let's say we have a thermal power station of, let's say, uh, and small industry, let's say, an iron concentrated power or the current density that is required there. For that, if we require, you try to use solar energy, can we in requires to be stored. The problem with solar energy is not just harnessing it, but its storage. Obviously, when we talk about energy storage, we have a situation where solar energy can be stored in a more environmental friendly way. We are going to have limited use of solar for small clusters. Let's say for a household for certain things, yes, all those is fine. But large scale use we form in course of time, not today. Geothermal and tidal, well, these are geothermal. Obviously, we do not have much. Tidal, yes, but tidal energy, the general observation I can tell you off the record, the general observation is that the amount of infrastructure and the amount of maintenance cost that it requires is much higher than the cost of electricity generated through it. It requires a lot of technological inputs at this point. So where talked about thermal, gas and thermal is all the same, oil, gas, thermal. They are same, they are using either the hydro. But now here we are coming to nuclear plant. Nuclear plant is something totally different. Ability of the fuel. See, when we are talking about large term energy inputs, large energy producing units, there are two aspects to it. First is availability of the fuel, and second is what is the environmental impact of that unit. So, obviously, whenever you are burning carbon or hydrocarbon, the environmental impact is very, very large. This is something which is much different from nuclear energy, where the carbon footprints are very, very less. That means the carbon footprints are less, meaning that the environmental impact of nuclear energy is almost negligible as compared to any of the thermal gas based or gas or oil, fuel oil, these three based. All of them contribute to carbon dioxide. All of them contribute to sulfur dioxide. All of them contribute to carbon monoxide. And the amount at which it is going up, have a just look. Year 1800, it was 280, 580 ppm. This is going to be where a person will be not able to live very happily at these levels of carbon dioxide. This is very alarming, right? This is a fossil fuel addiction. Now, this is the most important point here. Another 50 to 70 years, we are going to run out of coal. Where do we go then? Forget the sustainability, forget the environmental impact. We don't have anything to start with. Where do we land up? Are all our power requirements going to come down by another 50 years? No. As we stand, the population is rising, the requirements are rising. Our requirements are not only going to be static, they are going to grow at an exponential rate. We'll come to that a bit later. Sorry, I'm just talking to you as a part of a energy story. So this is how the energy scenario looks. So this we have already discussed. I think we need to go into details of this. This is what a viable energy source should look like. Carbon-free technology, or at least lower greenhouse emission, acceptable levels on, and the first one, long-term sustainability to support a growth of economy at 8 to 10%. This is what the world economy and Indian economy is slated to rise. if our energy required generation capacities do not match up, we will lag behind this and the development will be stalled. So these are the basic requirements of any energy source which is sustainably used. Now, third aspect is lifetime, like I was talking to you. This is not exact, but a rough estimate of different resources, how long they will last in years. Oil, another 50, 60 years. Gas, slightly over that, 75 years. Coal, world coal. This is not talking about Indian coal is going to last even lesser, about 150 years. Now, this is what I have written here is U oblique LWR, that light water reactors. The most of the reactors that are functioning in India at this point are are ULWR direct. Okay, so they can have a sustainability of 70 years. But once we go in for stage 2 and stage 3, I will come to that later in nuclear energy program, then we have got a sustainability. Just see the quantum jump. This is beyond the scale, so I stopped here. It is 4,000 years. So from somewhere about 150 years, we are now scaling up our viability, possibility of energy generation to 4,000 years. This is the beauty of nuclear energy. Obviously, I would say, with all that in mind, anyone would say nuclear energy is one of the major, I would not say the only, one of the major clean energy options. Okay. We'll skip this. Sorry, the slight problem with the slide. Now, per capita country's prosperity is often equated to its per capita power consumption. Have a look. Norway seems to be having highest, Canada, USA, and this is where we stand, India. Thankfully, we are slightly better than Bangladesh and well below the world average, Bangladesh and Sri Lanka. So until our per capita electric consumption goes up, that's an indicator of development. I would not say the only indicator, but one of the indicators of development. So we have to move from here to somewhere at least here. So this progression will require so many energy sources, out of which nuclear energy is going to be one of the major ones. As I was talking to you, how our energy consumption has grown. Hope you can see the slides, Doctor. Can you see them clearly, or I have to put it in full screen mode?
Sir, it's clear, sir.
Fine.
Screen is
I don't
clear,
have
sir.
to. I don't have to put it in full screen mode, na?
No, sir.
Okay, fine. So, see, when as an prehistoric man, this is where about 300 to 350 times rise in our energy consumption has come. 100 times the energy is a primitive man today, and we are aiming here. So, about 300 times. Where the energy is going to come from, we have to generate it. This is the dire requirement of some coming years. All our technologies will fail if we do not have. That's why I'm coming to uranium. See, uranium it was formed in course of giant stars. Then, when the Earth was formed, this ancient dust was drawn into the planets, and now it is with us. So all that is fine. That is the historical aspect. When naturally uranium, when you come to say uranium is present in nature, it is present in these three isotopes: uranium 238, 235, and 234 at these percentage levels: 99.28, 0.71, and 0.005. Okay. The irony is that the present stage 1 reactors, nuclear reactors also, use 0.711% of the uranium available to us. One which is easily fissile and does the job for us. For uranium 238, we are proposing, and already it is in working format, the stage 2. We'll come to that now. So you just see 99.28% of uranium that is present on Earth is in the form of uranium 238 isotope, 0.71 in 235, and 0.005 in 234. This is not significant in terms of power generation. These two are definitely going to be the main workhorses. Uranium is actinide. I will not go over its chemistry much. You can, all of you can even see it, and many of them. Now, this is the difference. The natural concentration of uranium in Earth's crust. Crust here, we have got our own systems here, own locations. Second one, which is going to be of major utility in nuclear power generation, is thorium deposits. This is a technology which is growing. Already its prototype is working. This is one technology which is India centric. Not many of the world's nuclear states also are doing any work on it because they are not having this as a raw material with them. This is one raw material which is almost exclusively, I won't say completely, almost exclusively available with India, which can be turned into a fuel. Thorium directly cannot be a nuclear fuel, it is not fissile. It has to be converted into a nuclear fuel, which I showed you, if you remember the slide, about 400 years, 4,000 years longevity. This is one stage which will give us. Program which was envisaged by Dr. Bhabha way back encompassed the use of uranium 235 plus, subsequently U-238, and then thorium. All the three available situations in India, he has DAE, Department of Atomic Energy now has a complete program. It is already working. All the three types are reactors are working. The major are the first type. The two others are coming up. Two others in the sense where thorium gets converted to where uranium 238 gets converted to plutonium, and where thorium gets converted to U-233. That is coming up. They are unstable. Let's skip this. We'll get straight away to this. This definition, big definitions, bookish definitions, they are already there. We have discussed them. But here the main thing that is to be said, normally our media, press and whatever vernacular media, press media, English media, they are very lax. And unfortunately, I shouldn't say that, but they are very lax in their scientific reporting. They try, in fact, to increase their circulation, TRP. They try to sort of make nuclear power look like something that is very, very dangerous, or something that is going to cause you an harm. However, if you go through, somebody goes through the records, the safety record of nuclear energy is better than any major industry in the world, whether it is manufacturing or power production. In fact, far, far superior than the coal industry. Okay, but our media hype is a very difficult proposition. Now, all these factors, you just if you can read them, you go through them. We'll come to them point by time when I just get to that location. Okay, sorry, just yeah. Disadvantages of coal: limited world poor ash quality. You must have seen all those fly ash dunes around the power stations. Nowhere in the nuclear industry you will see that. In terms of the same power production, 1,001.5 million kg coal is equivalent to 1 kg of uranium. This is 1.5 million kg coal to 1 kg of uranium. So this eco-friendly need not be even emphasized. It is implied right there. Just have a comparison. Quantity of electricity per 1 kg of fuel, tons of fuel required for these the other two aspects. 1 kg firewood, 1 kilowatt approximate. 1 kg coal, 3 kilowatt. This is when I'm talking coal and firewood, it's complete burning. 1 kg oil, 4 kilowatt. 1 kg uranium, 50,000 kilowatts. Here, mind you, I'm talking about 1 kg uranium. Okay, and just look at the bottom line, because we had used only 0.71% of that in the first stage. So when we utilize the remaining uranium, this is what is going to come out: 35 lakh kilowatt hour from 1 kg of uranium. Correspondingly, obviously, the tonnage required for 1000 megawatt plant will be very large. 1000 megawatt plant from coal requires 2000 train cars once through. I'm talking about this aspect. This aspect will be not talking about it here. Just giving you a comparison with uranium and others. Now, idle, nuclear, and coal fired. Idle, both submergence is 2,000 to 5,000 hectares, waste in fuel less than 1 ton. Have a look at coal, 70 hectares, coal 2,60,000 tons, that is 5 train loads per day. And what is the emissions coming out? So many tons of carbon dioxide, sulfur dioxide, NOx, and this is the worst part, 1.2 million tons of ash. What is the Now, I don't know how many of you really are aware how a nuclear reactor works. Just a very basic, I will talk to you. You must have seen the thermal reactor work wherein water is heated, converted into steam, and the turbines are rotated, giving you the electricity, right? In short, that is a very simplest way of saying electricity is generated by steam, which is which turns the turbine. In nuclear reactor also, it is the steam which turns the turbine. There is not much difference. The difference is in the way the steam is created. In thermal reactors, we use large amount of coal, oil, gas to burn, and it is burned to give the energy. Here, the nuclear fission reactor takes place. That fission reaction gives you the energy, which is then passed on to the water through the connecting pipes, and then this water gets heated and turns a turbine. So the right part of the slide remains the same. It is this zone where the nuclear energy comes into picture. Nuclear energy doesn't create energy in any other way, the same way as the thermal. Only the heating mechanism of the or the way the steam is formed differs. Now we'll get to this slide slightly later. Okay, this had put in, but I think we had talked about it already. This also we can skip. We can get to it later if you want. Now this is our present situation. 64%, 65% is thermal, 21% is hydel. This is renewable. Sorry, you are not able to. Coal is going to exhaust. Hydel, it is seasonal, as I told you, only 5 perennials. Renewable, this share in over the years is definitely going to grow. So these are the two sectors where energy inputs are going to come in some years from now. These two sectors, the things are going to go down. Not because they are bad. Yes, to thermal, they are not bad. They have their own problems. See, as I told you, the heating up is done by this one. Requires fuel production, same amount. One atom of carbon gives 4 EV, one atom of U235. Mind you, this is U235. 200 million electron volts. This is a large amount of energy which comes up. And that is why we require very small quantum of fuel for giving up the energy. Please go through them. This is one major aspect. And the best part of the entire story is that nuclear fuel cycle of India is indigenous, starting from the raw material to the finished product to the disposal of waste. It is all minerals. These minerals are then processed, milling, mining, converted into fuel, made into fuel rods, then subsequently taken up for reactors, and again the used fuel is again taken back. It is not spent fuel storage. From there it is again taken up, refurbished, and again used. So this cycle continues. This may be slightly off. This figures may be slightly off because the present annual report is yet to come. This is the present generating capacity. It might have gone up slightly if this year is about to come. Yeah. Now this is I'm talking about stage one, stage two, stage three. I just talked to you. Stage one, we are using uranium 238 that is converted to plutonium 239. Uranium 238 is also present in stage 1, while uranium 235 is getting fission. Uranium 238 is also along with it, that gets converted to plutonium 239, which is fissile in nature. So that plutonium 239 is used in stage 2. This is what I was talking. Stage 2 and serves as a fuel. Now in stage 3, while this is happening, what we do along with the core, along the sides, we call it blanketing. So if a container is there, the central is the heating mode. Along the edges, we blanket it with, in first case, with the fuel itself. In the second case, we blanket it with thorium. This thorium now gets converted to uranium 233, which is again fuel, which is fissile. So we have got these three stages. We are majority in the first stage. Second stage, we are already generating. Third stage also, we are about a 30 kilowatt exploratory reactor and AHWR at Kalpakam. These are the two stages which are going to give us the sudden leap that we require. And we are almost there now. Well, Einstein equation of E is equal to mc square is a savior for many, and it has been of much use in the atomic energy. See, just have a mass balance. If you see, uranium 235 undergoes fission, it gives almost equivalent uh, two or three or six different products. So one of the product range is krypton and barium. Another product is molybdenum 95 and lanthanum 195. In all cases, what happens if you take the mass balance, left hand side of the reaction and right hand side of the reaction, the difference is 0.2194. Sorry, it's gram here, it is wrongly written. It should be AMU. This mistake has occurred here, 0.2194 AMU. Now this, when multiplied with velocity of light, is going to give you tremendous power, square of velocity of light. So delta M will be this into T square. So that is where you get fission of 1 gram. Just have a look. 1 gram of uranium 235 per day generates 1 megawatt power. This is something which is unheard of in any thermal reactor. This sort of a current density, power density is not possible. Second stage, as I told you, plutonium 235, we can have the reaction. Here we do this additional. Okay, thorium 233 is also put in the surrounding blanket. Thorium goes to, see, I'll just go one slide behind. Here what we did, uranium 238, 239, we'll put in some thorium. This thorium will get converted to U33 and serve the purpose as fuel in stage 3. So they are all interlinked. Stage 1 followed by stage 2 by stage 3. And this is, mind you, this is all indigenous. Let's not go into the details at this time. So we are, okay, we'll skip this slide as I think we are getting short of time. We'll go through this. Okay, sorry, just one slide where I'll show you. These are some of the locations where uranium mining in the country is being carried out. West Khasi Hills, Meghalaya, we have a large deposit. Unfortunately, because of certain issues, the mining there is not possible. Shouldn't say officially, but yes, non-scientific political issues. Singhbhum Belt, Jharkhand, this is where the major Jadugoda mines is there. Then one major location that has come up in Andhra Pradesh, that is Kadapa district, Andhra Pradesh, and Nalgonda. These are the two major. We are having a large amount of source material also with us. Nuclear option, it is the only power source, mind you, where multitude of applications for human and societal use. Till now, we have been talking only about power, energy. Now let's look. What apart from energy, what does medicine? Technetium 99, any of the scanning technologies, radiopharmaceuticals, these are the spin-offs of nuclear technology. So this is one situation where no other detection of pipeline leakages. This is very significant. I'll just show you, particularly when the pipelines are buried. You don't have to, yes, if I got, yeah. If the pipeline is buried, I don't have to bring out the entire pipeline to see where the leakage is there. Send a radio tracer through it, monitor it, and then you can ascertain the zone where the leakage has occurred. Only bring up that area, repair it, and again send it back. It helps in reducing the maintenance time and the maintenance cost, a great effect. And not only that, it protects the environment in that way. These are the multitude of uses of nuclear energy that are being practiced in India. Industry, nuclear batteries, smoke detectors, petroleum industry, luminosity, powering satellites. I have not written one more thing here, that is powering your submarines. So the spin-offs are equally large. Spin-offs are very large. So apart from the power generation, which undoubtedly it does without harming the nature, it adds up to give you a quality of life. Just some of the photographs of the different products. We talk about India being an agrarian society. So many new either using mutation breeding, and they are already handed over to the farmers and they are reaping the benefits out of it. It's not that technology is developed and put only for just a recap of the comparison that we had. I think we can skip this. So this is apart from energy and power. Conclude, I would say at present the GDP is so much, population is going to go up, power requirement will be greater than 1000 gigawatt electricity. Conventional source cannot sustain it. Indian closed nuclear cycle, what I shown you from stage 1 to stage 2 to stage 3, that is what is called closed cycle. That means the fuel doesn't go out of the system, it is going from one system to another. We are not removing the fuel completely out. So gentlemen, I conclude by saying sustainability, believe me, is not a slogan. It is the most important aspect if we as human race is to survive. Thank you. Thank you all. Any queries or anything related to that? I'll be happy to answer.
Thank you very much, sir, for such an excellent and informative session. There are few questions, sir.
Sure,
So
please.
one is which renewable source energy is the best?
Okay, I got the question. See, like I discussed, the most easily available low cost energy that is made available to humans is solar energy. Now that is going to help us and going to sustain human life. It sustain human life and it will sustain human life in years to come. However, the problem is how to harness it. साध्या ह्याच्यात सांगायचं, मराठीत सांगायचं झालं कोणाला, तर सनलाईट आहे, सनलाईट मधून एनर्जी तुम्ही ठेवणार कशात? You require batteries. Now, how large battery sets can you have? Isn't it? And
Yes.
battery sets are themselves going to cause a lot of pollution. So, like I discussed earlier also, until a technology is developed to harness and store the solar energy, there is no doubt that the cleanest form of energy available as of today is solar energy. But while we are harnessing it, while we are capturing it, while we are storing it, we are creating enough problems. So we have to have an eco-friendly system where solar energy can be harnessed. That is where, so solar energy is going to give us the largest part because that is only visible, distributed all over. Okay, anything on that?
Sir, there is one more question.
Sure.
Which why renewable energy good for climate change?
I couldn't get the question. Please repeat.
Why renewable energy good for climate change?
Okay. See, climate change is a consequence. One has to understand. Climate change is the result of human beings inefficient, unthoughtful behavior in terms of energy scenario. We never bothered what we are doing. We only looked at the present at that time. I want energy. I will burn wood. I will get lot of energy. We did that for ages, for thousands of years. We have been doing that. Now, Earth's atmosphere has is getting slowly saturated with carbon dioxide and other noxious gases. If this continues beyond a particular point, it is going to be harmful for the entire population. That is why renewable sources means what? They are sustainable. It means their impact on the environment is low. That is why renewable sources are being projected, wherein the renewable in the sense what you use something, energy is drawn out of it, again you can reuse the same thing and again have a continuous draw of energy for it without allowing the environment to be polluted. That is the reason renewable sources are very very important, like solar or wind. But I think if you remember, we discussed the present problems that are there. In principle they are very good, but their utility at a particular point, for a particular country, for a geographical location, has to be seen before they are implemented. Okay.
So, last question, sir. How long does it take to replace non-renewable energy sources? How long does it take to replace non-renewable energy sources?
That's a very difficult question to answer, because that will depend on how seriously we as human beings take the issue. Are we willing to get our energy requirements down at this point? If we are going to lower our power and energy requirements, then the requirement of energy is lower. Obviously, the conventional sources will be generating less. Renewable sources contribution will increase. So it depends. How much are we willing to lower it? And second, what are the environmental friendly options that come up? At this point, you cannot predict. At this time, I don't think you are able to predict that.
So one more question, sir. What's your view on fusion reactors? What is your view?
Yeah,
What is
correct.
your view on?
Correct,
Yes.
correct, correct. That is one topic I purposely did not touch here, because it is too deep a topic to be discussed with all things together. Yes, European Consortium of Asia, including India, are in the process of developing fusion reactor. Now, fusion reactor, I will not talk about sustainability there. I will talk about its eco-friendliness, because the material that is used there and the amount of material that will be used there are both in such a way that they will not pollute the environment. So yes, fusion reactors are going to play a major part, but I didn't want to discuss it here because it is still under experimental conditions. No no fusion power generation plant even at a laptop has been set up. The things are going on, they are very good indications, but and pilot plant basis also is not in existence yet, so it will take its own time. As and when, see, if you look at sun is nothing but a fusion energy solar plant. Solar energy comes out of nowhere but from the fusion. Similar, we can have small fusion plants here, but there are certain practical difficulties. One of the major difficulties is that when the fusion occurs, the temperatures are extremely high like a sun. So what is the containment? That means how to hold that mass together, fuse mass together to draw the energy. Otherwise, what will happen? Once there is no containment vessel, this concentrated form of energy will move away and nothing to hold it. It will go away, being you cannot draw energy from it. So the problem at that point is containment vessels. Different forms have been tried. Even magnetic fields have been used. High magnetic fields are known to hold the plasma. When fusion temperatures are reached, matter exists in the form of a plasma. So that plasma can be contained using electromagnetic high magnetic fields that is being explored, but still not at the generation level, commercially generation level. No, sir, it will take time. If it comes, and as and when it comes, it is always welcome.
Thank you, sir. Thank you very much. Now I request Dr. Niharika to give a vote of thanks.
Good afternoon, everyone. I, Dr. Niharika Gehlot, would like to extend my heartfelt thanks to Dr. Patwardhan sir for sparing his precious time and enlightening us with such an informative session on the occasion of National Science Day. It will be very helpful for all of us. With immense pleasure, I would like to thank our Honorable President Sir, Shri Sharadji Kalmek, and Honorable Secretary Sir, Shri Hemanji Kalmek, for giving us the wonderful opportunity to conduct this webinar. I would like to specially thank our respected Dean Sir, Dr. Mahesh, for his continuous encouragement. A special thanks to Dr. Deepak Nagpal Sir and our IT team for their efforts. Last but not least, I would like to thank all participants for their patient listening and to all those who were directly and indirectly involved in this venture. Thank you so much, everyone.
Thank you, sir. It's a small token of appreciation. So we'll be sending you through mail also and hard copy also, sir. Thank you,
Thank
sir.
you.
Thank
It has
you.
been a
Thank you.
pleasure to be associated with you all. Thank
Yes,
you.
sir.
I
Thank you,
hope it
sir.
has been useful, because normally when you go to a dental college, you are very afraid to open your mouth. Something will happen.